Electric appliances convert electricity into heat energy, providing you energy in a form that you can use. In this lesson, you will learn how electrical energy transforms into heat energy. At the end of this lesson, you will be able to describe the heating effect of electricity, identify the cause of the heating effect of electricity, illustrate the working of an electric fuse, state and derive Joule's law. When you switch on a bulb, the thin metallic wire or filament in the bulb turns red and the bulb starts glowing. This is because when an electric current passes through a metallic conductor, the conductor gets heated. Thus, electrical energy is transformed into heat energy. This is called the heating effect of electricity. Many appliances in our household utilize the heating effect of electricity. Some common examples are electric irons, room heaters, and storage water heaters. How does the electrical energy of current get converted into heat energy? Every conductor offers resistance to the flow of current. When a potential difference is applied across the ends of a conductor, the free electrons in the conductor start drifting from the low potential end to the high potential end. These electrons collide with the positive ions. That is, the atoms that have lost their electrons. When the collisions take place, the energy of the electrons is transferred to the positive ions, making the ions vibrate more violently. This creates resistance to the flow of electrons. The electric current has to overcome this resistance. The work done by electric current in overcoming this resistance is converted into heat energy. This is the heat that you use in your electrical appliances. Metallic conductors used in electrical heating appliances to convert electrical energy into heat are called heating elements. For example, the filament in a bulb is a heating element. A good heating element should have high resistivity so that it gets heated quickly, high melting point to enable it to withstand high temperature, negligible variation in resistance due to temperature changes. Three metal alloys most commonly used as heating elements are nichrome, an alloy composed of 80% nickel and 20% chromium; manganene, which is 86% copper, 12% manganese and 2% nickel; constantan, a copper-nickel alloy with 60% copper and 40% nickel. If your electrical appliances receive very weak or very strong current, they could be damaged and stop functioning. To prevent such damage from fluctuations in the current, an electric fuse is used in the circuits of most houses these days. An electric fuse is a safety device used to protect an electric circuit against excessive current. The mechanism of the electric fuse is based on the heating effect of electricity. You may have often heard people talking about replacing the fuse in their homes because the fuse blew, cutting off the power supply. An electric fuse contains a fuse wire that is designed to withstand a particular amount of electricity flowing through it. When the electric supply fluctuates and the current becomes too strong for the wire, it melts and breaks the supply of electricity. Electric fuses are rated according to the current that they can withstand. For example, a fuse rated 5 ampere can withstand current flow to the maximum of 5 ampere. If the current flowing through that circuit exceeds 5 ampere, the fuse wire melts from the heat, cutting off the power supply through that circuit. We can monitor and control the heat generated by electric current by regulating the current supplied to an appliance. James Prescott Joule, a British physicist, expressed the relationship between the heat generated in a conductor and the amount of current flowing through it. This relationship is popularly known as Joule's law or Joule effect. Joule's law states that the amount of heat produced in a conductor is equal to the product of the amount of current squared, the resistance of the conductor, the time for which the current passes through the conductor. To derive Joule's law, let a potential difference of V volts drive a charge Q coulomb through a heating element, and W be the work done. The potential difference is a measure of work done in moving a unit charge across a circuit. From this, we get equation 1. V is equal to W divided by Q, or W is equal to VQ. The amount of electric current passing through a circuit is the product of the rate of electric current and the time of flow. From this, we get equation 2. I is equal to Q divided by T, or Q is equal to IT. Substituting the value of Q in equation 1, we get equation 3. W is equal to VIT. Now let's use Ohm's law. V is equal to IR. In expression 3, to get the formula for the total work done by electric current. The total work done by electric current, W, is equal to I square RT. This work done by electric current to overcome the resistance of a conductor is converted into heat energy, which is represented by H. Hence, H is equal to I square RT. You have learned in earlier classes that power is the rate of work done, as energy is the capacity to do work. Energy and work are equivalent. Hence, we also define power as the rate of consumption of energy. In terms of electricity, the rate of consumption of electricity is electric power. When an electric current flows through a conductor, the rate of consumption of electricity by an electric circuit is also the rate of dissipation of electrical energy in the form of heat through the conductor. We have seen earlier that electrical energy is expressed as W is equal to VIT, or W is equal to I square RT. Hence, electric power can be expressed as P is equal to VIT by T. This implies P is equal to VI, or P equals to I square RT by T. This implies P is equal to I square R. Substituting V by R for I in the expression P is equal to I square R, and simplifying, we get electric power equals V square by R. The SI unit of electric power is watt and is denoted by W. 1 watt is the power consumed by a conductor having a potential difference of 1 volt across its ends when the current passing through it is 1 ampere. As watt is a small unit, for commercial purposes, we use a bigger unit, kilowatt. A kilowatt is equal to 1000 watts. According to the definition of power, energy can be represented as the product of power and time. For commercial purposes, the unit of electric energy is kilowatt hour, denoted by kWh. Simplifying the expression, 1 kilowatt hour is equal to 3.6 into 10 power 6 watt seconds. As 1 joule equals 1 watt second, 1 kilowatt hour equals 3.6 into 10 power 6 joule. There is no potential difference between the ends of this coil of wire. How then does the bulb glow? A magnetic field gives rise to an electric current in a conductor due to electromagnetic induction. In this lesson, you will learn how electric current is induced due to a magnetic field. At the end of this lesson, you will be able to explain electromagnetic induction through Faraday's experiment, state Faraday's law of electromagnetic induction, use Faraday's law combined with Lenz's law to find the direction of a current, apply Fleming's right-hand rule to identify the direction of an induced current, demonstrate the working of electric generators and explain domestic circuits. You just observed that there was no electric cell to maintain a potential difference across the circuit. Yet, the bulb started glowing. When the wire is moved across a magnetic field, the free electrons in the wire experience a force that makes them move through the wire, inducing an electromotive force EMF, and thus an electric current in the wire. This process of generating an EMF in a conductor by moving the conductor through an external magnetic field is known as electromagnetic induction. When a conductor is moved in a magnetic field or kept in a fluctuating magnetic field, the magnetic flux linked with the conductor changes. This change in magnetic flux induces an EMF across the conductor. The EMF generated in this way is called an induced EMF, and the resulting current is called an induced current. The phenomenon of electromagnetic induction was first studied by Michael Faraday. Michael Faraday hypothesized that current induced in a coil is due to a changing magnetic field. To test this hypothesis, he conducted an experiment. You can observe this experiment to verify Faraday's law. To conduct Faraday's experiment, we will begin by winding an insulated wire over a hollow paper cylinder to make a coil. Next, we connect a galvanometer to the coil. Finally, we insert a powerful bar magnet in the cylinder with its south pole entering the coil first. We observe that when the magnet is moved in, the galvanometer needle deflects towards the left. When the magnet is moved out of the coil, the galvanometer needle deflects towards the right. If the magnet is not moved inside or outside the coil, meaning the magnet is stationary, the needle immediately returns to zero. The deflection of the needle when the magnet is moved in or out indicates that a current has been induced in the coil. Thus, an EMF is induced in the coil due to the movement of the magnet. Faraday's experiment confirmed that a moving magnetic field is necessary for electromagnetic induction. The direction of deflection of the galvanometer needle depends on which pole is inserted in the coil first. For example, in the experiment you saw, if the magnet is inserted with north pole first, the needle will deflect in the opposite direction as that of the previous case. In Faraday's experiment, you observed that a relative change in a magnetic field induces EMF in a conductor. The magnetic field can be changed in two ways: by relative motion between the coil and the magnet, as you saw in Faraday's experiment, or by winding two coils on the cylinder near each other, as shown. In the second case, one coil is connected to a battery with a key. This coil is called the primary coil. The other coil is connected to a galvanometer and is known as the secondary coil. When the key is pressed, a current passes through the primary coil. This current produces a magnetic field. As the magnetic field around the primary coil increases, the magnetic field associated with the secondary coil increases equally. The change in the magnetic field associated with the secondary coil induces EMF in the secondary coil. This EMF can be observed through the deflection of the needle in the galvanometer. The quantum and direction of EMF induced due to electromagnetic induction depends on 5 factors. Let's examine these factors one by one. The first factor is the direction of motion of the magnet in a coil. This determines the direction of the induced current. If you insert the magnet in the coil, the galvanometer needle deflects in a particular direction. When you move the magnet out, the needle deflects in the reverse direction. Thus, the direction of current gets reversed when the direction of motion of the magnet changes. The direction of the induced current in the coil also depends on the orientation of the magnet. If you move the magnet into the coil with its north pole first, rather than the south pole first, the direction of the induced current in the coil is reversed. The speed of motion of the magnet through a coil determines the strength of the induced current. Thus, if you increase the speed of the motion of the magnet, the EMF generated increases, and vice versa. The strength of the magnet is another important factor. The quantum of EMF induced in a coil is proportional to the strength of the magnet. The stronger the magnet, the higher the induced EMF, and thus increased induced current in the coil. Finally, the number of turns in the coil also affects the induced EMF. Using a coil with a greater number of turns increases the induced EMF. Based on his experiments, Faraday postulated a law on electromagnetic induction. Faraday's law states that the induced electromotive force E in any closed circuit is directly proportional to the rate of change of the magnetic flux through the circuit. You can determine the direction of the current induced when a conductor moves in a magnetic field using Fleming's right-hand rule. This rule is also known as the generator rule. To use Fleming's right-hand rule, stretch the thumb, the index finger and the middle finger of your right hand so that they are at right angles to each other as shown. If the index finger points in the direction of the magnetic field and the thumb indicates the direction of the motion of the conductor, then the middle finger indicates the direction of the induced current in the conductor. Consider a conductor AB connected to a galvanometer placed in a magnetic field. The direction of the magnetic field is from the North Pole to the South Pole. When you move the conductor up, the galvanometer needle deflects to the right. This rightward deflection indicates the direction of the current in the conductor from end A to end B. If you move the conductor downwards in the magnetic field, the galvanometer needle deflects to the left. This indicates the direction of the current in the conductor from B to A. Thus, you can see that the direction of the magnetic field, the movement of the conductor and the induced current are at right angles to each other. Electric generators are based on the principle of electromagnetic induction. Generators are used to generate electricity in power plants for transmission and distribution of electricity over power lines, and to produce electric power required for aircrafts, ships and trains. Dynamos used in automobiles are similar to generators, but they produce relatively less power. There are two types of electric generators: AC generators and DC generators. An AC generator is made up of four major components: an armature consisting of a laminated soft iron core with copper windings with a large number of turns, two slip rings made of gunmetal, which are connected to the two ends of a coil and rotate with it, brushes to provide electrical contact between the external load and slip rings, and a powerful horseshoe magnet or an electromagnet. Now let's examine how a generator works. The rotation of an armature, PQRS, between the magnetic poles results in a change in the magnetic flux linked to the coil. This induces a current through the armature. Here is a step-by-step account of how the current is induced. Initially, the coil is vertical with PQ on top and RS at the bottom. This coil is rotated clockwise so that PQ goes down. As the coil rotates through 90 degrees, it becomes horizontal. At this stage, the change in flux with respect to the initial position is maximum. Hence, the current rises from 0 to maximum. The direction of current through each arm can be found using Fleming's right-hand rule. The current flows from brush B1 to brush B2. On rotating further by 90 degrees, the coil becomes vertical again. But now PQ is at the bottom and RS is at the top. The change in flux with respect to the initial position is 0. Hence, the current falls from its maximum in the same direction and becomes 0. Rotating the coil by another 90 degrees causes the current to increase in the opposite direction. Now the coil has rotated through 270 degrees from its initial position. Now the current flows from B2 to B1. On turning further by 90 degrees, the coil completes one rotation of 360 degrees. The change in flux with respect to the initial position is zero at this point. Hence, the current falls in the same direction and becomes zero. Thus, the current rises and falls for every 180 degrees of rotation of the coil in opposite directions alternately. The faster the coil turns, the greater the frequency of the current produced by the generator. In an AC generator, the induced current changes its direction periodically and is therefore called alternating current. An AC voltage is continually changing between positive and negative. The rate of change in the direction of the current is called the frequency of the alternating current. It is measured in hertz, that is, the number of cycles per second. The increase in value from 0 to the positive maximum, then the decrease back to 0, then the further increase to the negative maximum, and the decrease back to 0 is counted as one complete cycle. Like an AC generator, a DC generator also works on the principle of electromagnetic induction. However, a DC generator produces direct current and is commonly used in small-scale power generation devices such as a dynamo. A DC generator is equipped with a commutator, which is a pair of split rings, in a position similar to that of slip rings in an AC generator. A commutator helps in keeping the polarity of the brushes the same to ensure unidirectional current. The other major components of a DC generator are similar to that in an AC generator. A DC generator that contains a loop generates a pulsating DC current. To produce a more stable output, a coil with more turns is typically used. In a DC generator, when the coil rotates through 90 degrees, the change in magnetic flux induces an electromotive force of maximum strength. This current flows through the split rings to the brushes. When the coil is rotated further, at 180 degrees, the electromotive force becomes zero. At this point, the contact between the commutator and the brushes is reversed. The first brush now comes into contact with the second segment, while the other brush comes into contact with the first segment of the commutator. This keeps the current going in one direction. Most of the power plants in the world produce high-frequency alternating current that is supplied to industrial and household consumers through power grids. Electrical components and wires fitted in a household to supply electricity to various appliances form a domestic electric circuit. Let's see how electricity is distributed through domestic electric circuits. A network of overhead or underground cables brings power to our homes. Domestic electric circuits are connected to this network through mains supply cables, commonly known as mains. The mains supply cable has two wires. The first wire, usually in a red insulation cover, is called a live or positive wire. The second wire, insulated in black, is called a neutral or negative wire. Electric current enters a domestic electric circuit through the live wire. The neutral wire provides the return path for the current out of the circuit. These wires pass through the main fuse in a meter board. A main switch connects these wires to the line wires in the house. Line wires supply electricity to all circuits within the household. Separate circuits may be used for power lines supplying 15 ampere and 5 ampere current. This is to provide for varied current requirements of appliances. Appliances with higher power ratings, such as air coolers and geysers, require a 15 ampere supply. On the other hand, electrical fittings such as bulbs and fans run on 5 ampere supply. Domestic electric circuits also have earth wires used as a safety measure against any leakage of current. In case of power leakage, appliances with metallic bodies such as electric irons and water geysers may convey excess current to a human body in contact. This can result in an electric shock and may at times also prove fatal. Connecting the metallic bodies of these appliances to earth wire ensures that any current leakages are conveyed to the earth. Hence, earth wires save users from severe electric shocks. Earth wires are generally insulated in green color. An electric fuse is an important component of all domestic circuits. An electric fuse is a safety device used to protect an electric circuit against excessive current. If your electrical appliances receive very strong current, they could get damaged and stop functioning. To prevent damage from fluctuations in the current, an electric fuse is used in the domestic circuits. In a country like ours, economic growth depends not only on the amount of power produced, but also on how efficiently it is transmitted. Let us now understand how power is transmitted from one place to another. Electricity is generated at thermal or hydroelectric power stations. In power stations, mechanical energy is converted into electrical energy using generators. Generators work on the principle of a dynamo and produce large AC voltages. The advantage of AC voltage over DC voltage is that its magnitude can be easily varied with the help of a transformer. Hence, power stations have generators that produce AC voltage. Let us now understand with an example how transmitting AC is more advantageous than DC. Say, a power of 44,000 watts is to be transmitted from a generating station to a city or town hundreds of miles away. Since power P is equal to VI, where V is the voltage and I is the current, it can be transmitted at a voltage of 440 volts and current 100 amperes, or at a voltage of 11,000 volts and current 4 amperes. You know that the heat Q produced in a resistance R, due to the flow of current I through it, is equal to I square RT. Thus, if I is more then the heat losses are more. Thus, the voltage of AC power can be increased to reduce the current for the same amount of power to reduce heat losses. That is why it is advantageous to transmit AC power at high voltage and low current. In the example, it will be better to transmit 44,000 watts of power at 11,000 volts at 4 amperes than transmitting it at 440 volts and 100 amperes. Now let us understand how power is actually transmitted from a power station to our homes. Electricity is transmitted to our homes through a power grid system. The grid consists of pylons or towers to which high-tension HT transmission lines called HT bare conductors are attached. A group of pylons can receive power from different generating stations. They, therefore, form an integrated power supply system. Such a network of HT supply system in a region is called a power grid. Power stations from different parts of the country are connected to the grid. This form of overhead transmission of electricity is employed for covering large distances. Here is a schematic diagram of power transmission. At the generating station G, a voltage of 11,000 volts, 11 kV is produced. A step-up transformer T is used to convert this AC voltage into a higher voltage of 220 kilovolts or 132 kilovolts. This high voltage is transmitted to a branch station outside a city called a major load center. At the major load center, the high voltage is reduced to 33 kV using a step-down transformer. At an intermediate load center, it is further stepped down to 11 kV and is supplied to substations. This 11 kV power is stepped down by local transformers to either 415 volts or 220 volts and then supplied to industrial or domestic consumers. Note that all houses or industries are connected in parallel to the main supply. Thus, power transmission is done efficiently using step-up and step-down transformers.
Looks like the circuit is working.
Ouch! The bulb is hot.
Careful, Tina. Yes, the bulb is hot.
In this lesson, you will learn about the heating effect of electric current. At the end of this lesson, you will be able to explain the heating effect of electric current, identify the appliances that use the heating effect of electric current, and explain how an electric fuse uses the heating effect of electric current.
Let's see why the bulb is hot. Let me first switch off the bulb in this circuit. Tina, touch the bulb and tell me if it's hot.
James, the bulb is not hot. It's cold.
Good. Now I will let current pass through the circuit by switching it on. Now touch the bulb again and tell me if it is hot.
Yes. Now the bulb is hot.
That's right. So, can you guess what heated up the bulb?
Let me see. The bulb was not hot at first. Then you switched on the current. And now the bulb is hot. Of course. It's the electric current that heated the bulb.
That's absolutely right, Tina. When an electric current flows through the filament of the bulb, it produces heat. That's why the bulb becomes hot. So, never touch a lighted bulb. This property was studied by James Joule in the 19th century and is today known as the heating effect of electric current.
Did you know? An electric bulb is used for light, but part of the energy received by the bulb gets used up due to the heating effect. Thus, some electricity is wasted. Using compact fluorescent lamps or CFLs in place of ordinary bulbs can help minimize wastage of electricity. CFLs do not use a filament. That is, they don't depend on the heating effect of electricity to provide light. Light is produced using two electrodes. Fluorescent coating on the inside of each tube helps make the light brighter.
There are many appliances that use the heating effect of electric current. Typically, these are electrical appliances that are used for heating things. Can you recognize any such appliances in the store?
That's easy. I know many such appliances. There's the electric iron, electric room heater, toaster, hair dryer, electric stove, geyser, immersion water heater, and food warmer. In fact, I don't know how I would manage without my electric room heater in the winters. Ugh.
That's right. Many appliances use the heating effect of electric current. Take a look at this toaster. After I switch it on, the coils of wire inside the toaster turn to a bright orange-red color, as if they are on fire. This is because of the huge amount of heat being produced. Such coils of wire in the appliances are known as heating elements.
What's this sign on the toaster?
That is the ISI mark, which stands for Indian Standards Institute. It is the mark of quality. We should always buy appliances having an ISI mark, as it ensures that the appliance is safe and will not waste electrical energy.
Okay. I can see the heating element in the toaster and the bulb. But what about the geyser and the iron? Where's the heating element in these appliances?
The element in these appliances is inside and not visible on the outside. I can show you the heating elements of different appliances.
They all work on the heating effect of electric current and yet are useful in so many different ways. We seem to be using a different kind of element for every appliance.
That's a good observation, Tina. Yes, the heating elements of different appliances are different. The element chosen depends on the function of that appliance. Some appliances are required to produce more heat than others. The amount of heat produced in a wire on passing an electric current will depend upon factors such as the length, thickness, duration of flow of current, and the material of the wire. For example, the amount of heat that is required to be produced in a hair dryer is much less than the heat that needs to be produced in an electric toaster. Thus, both these appliances have different elements made according to their needs. So, depending upon the amount of heat that needs to be produced, the length, thickness, and the material of the wire in elements vary.
So, if I were to use a very thin wire, and if a large amount of current passed through it, the wire could get very hot and melt. Is that correct?
That's absolutely correct. In fact, a safety device called the electric fuse works on this very principle. Do you know what a fuse is used for?
Not quite. I've very often heard Dad say the fuse is blown when we have a power cut.
A fuse is a safety device that prevents damage to an electric circuit when excessive current passes through it. Damage to an electric circuit could lead to a fire. Let me connect the circuit. I will use a thin copper wire to show you how a wire can melt when a large current passes through it. Let me switch on the current in the circuit. See, Tina, when a strong current starts to flow through the thin copper wire, the heating effect of electricity melts the wire. Thus, the circuit breaks. An electric fuse is made of a wire of special material. It melts and breaks quickly when a large electric current passes through it.
How does the fuse help in preventing fire in our houses, though?
As soon as the current increases beyond a certain limit, the wire in the electric fuse melts and breaks off. This breaks the circuit. The circuit becomes incomplete and the current stops flowing through the circuit of our houses, thus preventing fire. When the wire in the fuse breaks, the fuse is said to have blown.
Oh, that's why whenever there's no electric current in the house, we hear people saying that the fuse might have blown off.
That's right. Different types of fuses are used based on the situation. Some fuses are designed for use in buildings only, while others are designed for appliances.
Caution! Never investigate a fuse on your own. Visit an electrical shop or ask your electrician to show you a good fuse and a blown-out fuse.
One more question. Why would the current exceed the maximum limit at any time?
It could happen due to several reasons, the most common being connecting many appliances to the same socket. The load on that socket increases as many appliances are drawing current from it, and there may be an overload in the circuit. Another common reason for excessive current is the touching of two wires directly due to wear and tear of the insulation on them. So, when two such wires carrying current touch each other, there's a spark, which could lead to a fire. This is commonly referred to as a short circuit. Both overloading and short circuits can cause a fire if a fuse is not used.
I don't remember seeing a fuse on our main board the last time the electrician had opened it.
That's because nowadays, a majority of the buildings use a miniature circuit breaker or MCB instead of fuses. These are switches that switch off automatically either due to overloading or short circuit. After rectifying the defect in the electric circuit, we turn the switch back on and the current begins to flow again.
Oh, so we don't need to replace any wire in MCBs, unlike what we have to do in a fuse when it blows off.
Yes, that is one of the major advantages of using an MCB. The important thing to remember while buying electric components like MCBs is
that they should have an ISI mark, right?
That's right.
This brings us to the end of the lesson on the heating effect of electric current. In this lesson, you learned to explain the heating effect of electric current. Identify the appliances that use the heating effect of electric current. And explain how an electric fuse uses the heating effect of electric current.